In this screencast, we're going to explore line integrals and how they generalize the integral you're familiar with from first semester calculus. So first, an integral from first semester calculus represents area under a curve. The way it does that is if we have some function f, and we've got an interval from a to b, then the idea is this integral represents the area under the curve, and we get it by cutting the interval up into little tiny bits. Each of those intervals has width dx. Well, then we take a curve and we ask what's the height. It doesn't have a constant height, but it's almost constant over the interval, so the height is f. If I want a little bit of area, the idea is let's take the height and times it by a little bit of length, which means if I want total area, I should just add up the little bits of area, which means I add up f times dx. Once I've given the variable I'm going to integrate with respect to, I can actually give the bounds a and b on my integral. That's a review of first semester calculus and how we get the integral back then. The idea is we're going to take the interval, and rather than using an interval, we're going to use curves in the plane or curves in space and start integrating over them. So a line integral, we need an example. We'll take a function such as 9 minus x squared minus y squared. We know that function is a paraboloid opening downward. It starts at height 9, and when it hits the xy plane, it comes out radius 3. I also want to take a curve, r of t. Let's make it an ellipse, cosine t, 2 sine t. And so this one goes 1 out in the x direction, 2 in the y direction, and it's an ellipse that moves around in the xy plane. Well, above the ellipse, we can use the function 9 minus x squared minus y squared to give our heights, and we're going to look at the region in space above the ellipse. We'll keep the sides in place. We need a height that hits the paraboloid. It's kind of like a roller coaster, but we're going to keep track of the sides. A picture of this in 3D from Mathematica looks something like this. The idea is I'd like to find the area of this shape. So it's some kind of cylindrical, elliptical cylinder. It's kind of been chopped off on the top by something a little round. What is the area? So to find the area, the idea is we're going to cut the curve up into a bunch of little segments. Each of those has length, which we've been using ds, a little bit of length. Well, above each of those lengths, the height isn't constant, but it's almost constant, and we'll say the height is f. If I'd like area, the idea is let's take height times width. Bingo. So area is add up little bits of area, which is add up f ds. Now, anytime you see this ds, you'll often also see a c underneath it. The c stands for the curve. It's just a symbol that says I'm going to integrate along a curve of function with respect to length. Well, I need to know what this ds is. We've already seen it. ds dt, that's a change in length over change in time. That's speed, which means I know ds is speed times time. A little bit of distance is speed times a little bit of time. So this is really integrate the function times the speed times a little bit of time. And now that I've given a variable t, I can go back and ask what bounds should I put on the curve. We'll often put an a, b here. For this example, to go around the ellipse once, I need to go from 0 to 2 pi. So we're now just going to take this formula and show how you can use it to actually get the area of this surface. We know our function is 9 minus x squared minus y squared. We also have our curve, which is cosine t, 2 sine t. I need to find the magnitude of the derivative, so I'll find the derivative, which is negative sine t, 2 cosine t, and then we'll find its magnitude. So I square the sine, negative sine, giving me a positive sine squared. I square this term, giving me a 4 cosine squared t, and I now have my magnitude of the derivative, in other words, my speed. So if I want area, I've got to integrate f, which is 9 minus x squared minus y squared. I need my speed, which I've got, sine squared t plus 4 cosine squared t. And then I need a dt. Now, the t, I need bounds. There's 0 to 2 pi. So I'll add the 0 to 2 pi on. Now, because this is in terms of t, every variable should be in terms of t. Hold on, we've got an x and a y. They need to be rewritten in terms of t. Well, we go back to our parameterization, and the parameterization tells us what x is and tells us what y is. So this is x, this is y. I just need to put those over here. So we write 0 to 2 pi. 9 minus x is cosine of t. Y is 2 sine of t. And then I still need my ds, which is the square root of sine squared t plus 4 cosine squared t dt. Now, obviously, when you get used to this, you can skip writing this extra step, but that's essentially it. This is now an integral we can type into some calculator or computer, compute, and that is precisely the area of that surface, which in 3D is the area of the regions in here. That completes the screen cap.